In this video, we're going to take a look at section 2.6 on variation. There are essentially two main types of variation. There is direct variation and there is inverse variation, and then there's combinations of the two. In addition to that, the variation that occurs can vary as well. For example, things can vary directly with x, or with x squared, or the cube root of x. You can, it's customizable, if you will. So there's two main types of variation, but the thing that it's varying with can be customized. So for direct variation, excuse me, we describe that relationship as y varies directly as x, and given that description, the equation that models that relationship is y equals k times x. So you see the equation here, the formula, whatever you want to call it. K is the constant of variation, or the proportionality constant. And while it's a letter like x and y, it is not a variable. So usually I take a moment when I'm teaching this class face-to-face to explain that not all letters are necessarily the same. Some letters are variables, some are constants, and you've already experienced this. When you are finding a linear equation, that's y equals mx plus b. Y and x are your variables. Those numbers can vary, right? You can plug in x equals 1, you can plug in x equals 2, you can plug in x equals 3, right? X values will vary. And depending on what you plug in for x, you get different answers for y. So your y values will also vary. But m and b are not variables because they are fixed numbers. We just use m and b in the formula because we don't know what those numbers are yet. But once we've determined what those numbers are, we substitute them into that formula and they just go in permanently, right? They don't fluctuate for a given problem, right? So once you've determined that the slope is 2, it stays at 2 for that particular problem. It doesn't equal something else later in the same problem. It's equal to 2 and it stays equal to 2. So the slope is a constant. It doesn't vary within a given problem. It only equals one thing. And so that's what's going on here with k, right? K is a constant and it's equal to just one particular value in any given problem. And once you've determined what that value is, you take k out and you put that number in permanently because it doesn't fluctuate. It doesn't change to anything else. So x and y in this variation can change, but k does not change, right? K is a constant. So y equals kx. Now, what does that relationship look like? Well, the example I often like to give is, let's say you want to take a trip somewhere, right? And so you are on the highway and you are going 60 miles per hour. Maybe not the easiest number to work with, but we'll just go with that because it's somewhat realistic. And so let's say you are going to travel for a certain amount of time and you want to know how far you're going to get. Well, after 1 hour, if you're going 60 miles, now think about, we use miles per hour without really thinking about the literal meaning of it. But it literally means that's how many miles you will go each hour, miles per hour. So after driving 1 hour at 60 miles per hour, you will have traveled 60 miles, right? You go 60 miles in 1 hour. After traveling 2 hours, you will have gone 120 miles, right? You go 60 miles each hour. So after 2 hours, 60 plus 60 means you've gone 120 miles. After 3 hours, you'll have gone 180 miles. And after 4 hours, you'll have gone 240 miles. And I think this will be enough for us to make the point that I want to make. So this is an example of direct variation. And the relationship here is that if you double the amount of time that you drive, you double the distance that you go, right? So doubling the time doubles the distance. And we can see that here, right? If you double it from 1 to 2 hours, you double your distance from 60 miles to 120 miles. But you can also see it here from 2 to 4, right? that's also doubling the time, and the relationship holds true. It doubles the distance. And it doesn't just work for doubling. If you triple the time that you spend driving, so if I go from 1 hour to 3 hours, I triple the amount of time I spend driving, you will triple your distance. If you quadruple your time, you quadruple your distance. That is what direct variation is. That's the relationship that is the essence of direct variation. When you change x by a certain factor meaning doubling, tripling, whatever, you know, how do I want to say this? When you change x by a certain factor, it causes y to change by that same factor, not another certain factor, but so let me try that one more time. If you change x by a certain factor, it causes y to change by that same factor. Doubling x causes the y value to double as well. That is direct variation. So anytime you see that relationship happening, you know that's direct variation, and this formula will model that situation. Inverse variation is the opposite of that. I don't know, opposite maybe is not a very well-defined term there, but the way we describe that relationship is y varies inversely as x, or we could also say y is inversely proportional to x. So there's two different ways of saying it. The formula that describes that relationship, the formula that models that relationship is y equals k over x. So x goes in the denominator. K, again, is a constant, the constant of proportionality. And an example of that relationship would be, again, thinking of taking a trip somewhere, except instead of fixing your speed, let's say you fix the distance. So you know your destination. You know how far away it is. Let's say it's 300 miles away. That's a good number to work with for this example I've found. Let's consider your speed versus the time, right? So how fast you go will determine how long it takes to get there. So if we go back to our, realistic speed of 60 miles per hour, and you might say, oh, I go faster than that on the highway. But again, this is an average speed. You might have to slow down if you get behind, at least in Kansas, you have all these one-lane highways where there's just one lane in any given direction. You get stuck behind a slow-moving vehicle, it's going to slow you down. Also, you might have to make stops like to get gas, things like that. So while you might be actually driving 70 miles per hour most of the time, all of these instances of stopping, slowing down could bring your average down. So 60 miles per hour, I think, is a pretty realistic estimate, maybe a little low, but again, easy to work with. If you're going 60 miles per hour, how many hours is it going to take to go 300 miles? And I put miles per hour. I'm sorry about that. I'm doing something a little unusual. Usually I record my videos later in the day. It's first thing in the morning. Not that it's that early, but I did just kind of wake up and I'm obviously not fully alert. And you could probably tell from my mannerisms. So I meant to say I said 300 miles, but I meant to write 300 miles, but I put miles per hour. I apologize for that if that was confusing. So we're driving 300 miles. We're going 60 miles per hour. How long is it going to take for us to cover that 300 miles? Well, we almost found out over here, right? I stopped one short. But if I go 5 hours, I add another 60 miles to the distance I'll drive, and I hit 300 miles. So if I'm going 60 miles per hour, it'll take me 5 hours to go 300 miles, right? So it's going to be 5 hours. Now, we just happen to have the numbers over here to figure that out, but what's the math that helps us, how do I calculate that from these numbers? You divide. You take the distance that you want to drive, divided by how fast you're going, and that will tell you how long it's going to take. 300 divided by 60 is how you get 5. So keep that in mind, because what I'm going to do now is suggest we, for some reason, cannot go 60 miles per hour. We hit a blizzard, and that slows us down, and we are now only able to go 30 miles per hour. Now, of course, if there's a blizzard, you probably should just not even take this trip, but let's say it's an emergency. You have to get there. It's 300 miles away. Even with the blizzard, you just need to go ahead and hop in the car and start driving, but you can only go 30 miles per hour. Now, how long is that trip going to take? how long is it going to take to go 300 miles? It's going to take 10 hours, right? Again, divide. 300 divided by 30 gives me 10. Let's say, I'm trying to think what I could do here. Let's say you can only go 15 miles per hour, right? Because it's an even worse blizzard, right? Divide these, 300, divided by 15 is going to give me 20. And let's go one more example. Let's do 10 miles per hour. It'll take 30 hours to do that. Now, what's the pattern here? Well, if I cut my speed in half, so I'm cutting my speed in half. Well, that's actually, I don't know, this is kind of backwards from how I usually do it. I must have did these numbers in reverse order from how I normally do it. Let's look at it this way. If you go from 30 to 60, you are doubling your speed. If I double my speed, it cuts my time in half, from 10 hours to 5 hours. That is inverse variation. When you change one variable by a certain factor, it causes the other variable to change by the reciprocal or the inverse of that factor. So doubling your speed from 30 to 60 cuts your time in half. If you triple your speed from, let's say, 10 to 30, that's tripling my speed. It cuts the time down from 30 hours to 10 hours, which means it cuts it to a third of its original amount. Right? It was 30 hours to take the trip at 10 miles per hour. By tripling my speed, it's going to take that time of 30 hours and take a third of it. It's going to cut it down to a third of what it originally was, down to 10 hours. And so that is inverse variation. So changing x by a certain factor causes the y variable to change by the reciprocal of that factor. That is the essence of inverse variation. So if you notice that pattern, you know it's inverse variation, and this equation, this formula, will model that situation. Those are the main two types of variation. However, you can have combinations of the two. And one special combination they have a special name for is jointly. I'm really not a fan of this special keyword, because all jointly is varying directly with two variables at the same time. It just varies directly with both. So if you see the phrase y varies jointly as x and z, that means y varies directly with both x and z at the same time. So jointly just means directly with both, with two variables at once. Now, sometimes when students see that there's two variations, they will set up two different formulas, but you can't do that. When there's two variations being described relative to the same variable, it all goes together into one equation, into one formula. And so when I say y varies directly with both x and z, it's at the same time, and they have to, like, it's all interconnected. They have to all, like, relate to each other in a single equation. And this is how it looks. So if it varies directly, that variable goes in the numerator multiplied to the k, right? Just like it does here, right? When y varies directly as x, x gets multiplied to k. So if it varies directly with x and z, both x and z get multiplied to k. So if it varies directly, you multiply it to the constant. If it varies inversely, you divide the constant by that variable. So what you'll notice is you can have any kind of combination of variations, but the most common one is having a variable that varies directly with one thing and inversely with another thing. And so that's what this would look like. And this is, I'm saying it's a combination, and this is just one example of a combination, but it's by far the most common one. I don't really think we ever see anything different. But they could, for example, say, you know, y varies directly with this one, inversely with this one, also inversely with this one. You can throw in as many as you want. And just remember that if it varies directly, you multiply it to k. If it varies inversely, you divide k by that variable. Right? So here we have varies directly with x, so we multiply x to k. And inversely with z, so we divide k by z. So directly goes in the numerator, inversely goes in the denominator. And that's how you construct your formula based on that description. All right, So I just wanted, normally like what I've done in the past is I'll do one at a time, just directly, just inversely. But I think it's best just to kind of throw it all out there. So we just talked about every possible type of variation. So we just went over the concepts, and then we're going to do several examples of these various types of variation. As I already mentioned briefly a moment ago, varies directly is the same as directly proportional to. It's just an alternate phrasing. In fact, I don't know when varies directly became part of the lexicon of this type of problem, but I don't remember learning that. I remember learning directly proportional to. That was the standard way of describing it back when I was a young student, as far as I know. Either that or just, and I've admitted to this, I have a bad memory, so maybe varies directly was there, but I don't remember ever seeing that phrase. I always saw directly proportional to. So now it's interchangeable. So in this section, you're going to see both phrasings. One problem will say y varies directly as x. The next problem will say y is directly proportional to x. It'll switch between the two. And it's not that hard to adjust because the key word is the same in both of them. If you see directly, it means the same thing, whichever way they're saying it. All right. And same thing with inversely, same thing with jointly. And I see there's a little typo here with a quotation missing. All right. Variation problems have the following structure. So every one of these problems is going to have the same three levels to them. Or I shouldn't say they'll all have the same three levels. They have up to these three levels. So they all follow the same path, but they don't all go as far as level 3. So some problems are just level, I call them level 1 problems, which is you just have to find the formula and you're done. That's all the problem asks you to do is here's the description, construct the formula, and you're done with that problem. That's a level 1 problem. Some problems are level 2 problems where they ask you to find the value of the constant k and construct an equation. In order to get to level 2, you have to do level 1 first. So if they're asking you find the value of the constant k, first you have to find the formula that describes the relationship. Then you can do the work of finding what k is equal to. That's a level 2 problem. But to get to level 2, you have to do level 1 first. Some problems stop there. Some problems just stop at level 2. Once you find the value of the constant k, you're done. There's nothing else left to do on that problem. Other problems go to level 3, which is they ask you a question about one of the variables. So it'll say something like this. Y varies directly with x. That's level 1. And when y is equal to 5, x is equal to 7. That's level 2. That information is so you can find k. Then it will say, find y when x is equal to 11. And so you have to answer that question. But you can't answer that question until you've done levels 1 and 2 first. So in order to answer the question they're asking you, you first have to have the formula, and you have to have the number for k figured out. Then you can answer the question. And so some problems are going to be what I call level 3 problems, where they go all the way to asking you a question that you can only answer by doing levels 1 and 2 first. So every variation problem will have up to these 3 layers to them. And so that's just, they all, and that's kind of a nice feature of these problems is that they're kind of predictable in this way because they all look like this. Again, up to level 3. I'm having trouble describing that. They don't all go to level 3, but if they don't, then it's a level 2 problem or it's a level 1 problem. But this is just the structure of these problems. They will look like this, and they can go as complicated as just finding the formula, or I should say as simple as just finding the formula, to as complicated as answering a question given some information. So let me kind of show you what I mean. Maybe that's a better way to do this. So if y varies directly as x, that's describing the relationship between the two variables. From that, I can construct a formula. So this is to help me do level 1. And not only are these problems like predictable in their structure, the way the problems are described follow that structure exactly. So you can really just easily map, this is for level 1, this is for level 2, this is for level 3. They separate it with commas in this particular problem, right? If y varies directly as x, that's to help us find the formula. And y equals 7 when x is equal to 2. That information is given to us so we can find k. We can figure out what the constant is equal to. So that's level 2. What is y when x is equal to negative 8? That's level 3. We answer that question once we've done levels 1 and 2 first. So we have to go in that order, processing that information, doing the steps in that particular order that I just outlined. So for level 1, y varies directly as x. Whenever I see the word just directly by itself and there's no other variation in the problem, I immediately think of this formula. I just memorize it. Directly makes me think of y equals k times x. And then what I do is I change the variables based on what's given in the problem, usually. But for this particular problem, there's nothing to change because they're using the same variables in the formula I have memorized. They're using y and they're using x, which is what I already have there. But sometimes they'll have something like, w varies directly as b, And in that case, you would switch out the y for w in your formula and the x for b. So whatever letters are actually given in the problem, switch out x and y for those letters, right? And that's it. That's level 1. I have a formula that models this relationship based on the description that they gave me. Level 2 is to find k given this information. So the only way to find k is to know what x and y are equal to simultaneously. And that's exactly what they've given us here. Y is 7 when x is 2. So I know x and y simultaneously. I can plug those numbers in for those variables, and then I can solve for k to find out what k is equal to. So I'm going to plug in 7 for y, and I'm going to plug in 2 for x. And so I'm going to get 7 equals k times 2, and now I can solve for k. And I'll do that by dividing 2 on both sides. And unfortunately, I get a fraction, but that's just what it is. So k is equal to 7/2. Remember, k is a constant. So for this particular problem, it will never equal anything else. It can only equal 7/2. So once you've determined the value, it's stuck at that value. It will never equal another number for this particular problem. Now, when we move on to the next example, we'll have a different set of numbers. K will be a different value. But within that given problem, k is constant. It is fixed. So I don't need to keep using k in my formula because it's not going to change to anything different than 7/2. So once you know what k is equal to, replace it in the formula with the value that you just found. So we get y equals, in place of k, we'll have 7/2, and then we have x. Now you might be asking why why wouldn't I leave 7 plugged in for y? Because y is a variable. Y will not always equal 7. It will equal different numbers at different times. But k will always be 7/2. So I can go ahead and take k out, put that number in its place. But you don't want to do that with x and y. So even though I plug these numbers in for x and y to find k, that was only temporary. Once I have k, these things reset back to their variable letters. And the reason I'm pointing that out is because I have noticed over the years that students will give me this as their answer. They'll say 7 equals 7/2 times 2. So they're leaving the numbers plugged in for the variables. You don't want to do that. That's not an equation, right? This is a true statement, but it's not an equation. An equation needs to have variables. So you want to go back to using your variables, x and y. Do not leave these numbers permanently plugged in because these need to equal different numbers. In fact, that's what we have to do for level 3, right? So for level 3, we want to find what y is equal to when x is -8. So here x is equal to 2, but now we're switching to x equals -8 because x is a variable. It can equal different numbers. For level 3, it's now equal to -8. So we want to go back to using our variable letters here. Hope that makes sense. All right, so what we're going to do is take -8, plug that in for x, and then we'll find y. So we get y equals 7/2 times -8. Either use a calculator or you can reduce this, right? Think of this as 8/1. The 2 cancels out with the 8, leaves me with a 4. 7 times -4, don't forget the negative sign, is going to give me -28. Sorry, I wrote that 8 kind of weird. -28 over 1, but the over 1 part doesn't have to be written. And so we just get y equals -28. And that is it. That's the answer you were looking for. So that's what you type into the box here. So even though you do all of this work, setting up the formula, finding k, setting up your equation, it's all for the purpose of answering this question. And once you have the answer to the question, what is y when x is negative 8? Y is negative 28. That's what you type into the box, negative 28. That was the answer. That's the final answer. All right, let's take a look at another example. If a varies jointly as L and W, and a equals 30 when L is equal to 5 and W is equal to 3 square root of 2, what is a when L equals 6 square root of 3 and W equals 1/6? So again, I know it seems like a lot of information, but remember it breaks down into those 3 levels. It might reach all 3 levels, but like this problem, if you see 3 parts, that means there's probably 3 levels there, right? So this problem goes to all 3 levels. They're going to give you a hard time with the numbers you're having to work with. So that's one way they add a little extra challenge to this section. Not that it's necessarily easy, but they do like to give difficult numbers to work with. And you can see that here with the square roots and the fractions and all that. All right, but let's just start with level 1, right? So level 1 is that a varies jointly as L and W. Now, if you want, you can memorize the formula that we saw here, right, way back here, this formula here for jointly, right? So if a varies, or sorry, if it, I shouldn't say a, but if the relationship is varies jointly, you can maybe just have this formula memorized. Y equals kxz. That's where you want to start, right? So that's what I'm going to start with here. Y equals kxz, just to kind of demonstrate the thing I was trying to talk about in the last problem. Kxz. All right, so you start from that. That's the relationship. If it varies jointly, that's going to describe the relationship in the problem. But we're not using x, y, and z in the problem. We're using different letters. So we want to swap out the x, y, and z for what's actually being used in the problem, right? And so usually the phrases, or like the basic phrase is y varies jointly as x and z. But instead of y, we have a. So I'm going to make the same change in my formula. Instead of y, I will have a. And varies jointly as x and z, but instead of x and z, we have L and W. So I'm going to switch out x and z for L and W. And that becomes my formula, and that's level 1. Right? We have a formula now that models the relationship that's being described. Level 2 is to find out the value of the constant k. Right? And to do that, we need to plug some numbers in for all of the variables in the formula. So we have to know all of them, a, L, and W, simultaneously. So we need to know one instance of having the values of a, L, and W at the same time. And that's what they're providing here in the next segment of the problem. So this is level 2. A is equal to 30 when L is 5 and W is 3 square root of 2. All right, so I'm just going to write the formula again up here. And we're going to plug these numbers in. 30 for A, 5, whoops, pointing to the wrong thing. Sorry about that. 30 for A, 5 for L, 3 square root of 2 for W. All right, so we're going to have 30 equals K times L, which is 5. I'm doing a bad job of writing this morning. Times W, which is 3 square root of 2. So what I would do with this first is multiply these two numbers together. Right, so we'll have 30 equals K times, and with the radical there, it actually doesn't cause any issues, because when you're multiplying a number where there's a radical involved, and it's all multiplication. Now, I need to be careful how I say this, because if I was adding or subtracting here, it would be a whole different story. But since it's just multiplication, you multiply together what goes together. 5 times 3 gives me 15. And then the square root just copies down. So really you just get 15 square root of 2. Now to solve this for k, we will divide, since it's still multiplication, we're going to divide by 15 square root of 2 on both sides. And then we can reduce. Right? So it's going to be a fraction again. The 15 goes into the 30 and leaves me with 2. I kind of said that funny, but the 15 cancels out with the 30, but it leaves you with a 2 on top. And then the radical 2 will just stay on the bottom. Now, in most circumstances, Well, maybe we'll start. Actually, we probably still have to do something about that. I was going to say, in most circumstances, you want to rationalize the denominator. Sometimes with these problems, you can get away with not doing that. But now that I'm actually looking at the numbers we're about to deal with, we're going to have to rationalize this denominator. And you might actually be surprised what happens here with that. So let's make some more space below this to rationalize the denominator here. So the way you rationalize the denominator, we talked about this back in chapter 1, and it's coming up again here in chapter 2, at the end of chapter 2, but in chapter 2, you multiply the denominator by, when it's a square root, you just multiply the square root by a copy of itself. That always rationalizes the denominator. So I'm just going to multiply by another square root of 2. If I do that to the bottom, I got to do the same thing to the top. So square root of 2 times the square root of 2 is just 2. Again, I'm skipping a little bit of detail there, but it's a pretty well-known shortcut that when you multiply a square root to itself, the square root just goes away. Square root of 2 times the square root of 2 is the square root of 4, but the square root of 4 is just going to be 2. Right, that's what I get there. On top, these don't really multiply together, so I just write them side by side. I'll put the 2 first, and then I'll put the square root of 2 after it, because that's just the normal standard way of writing that type of number. And what happens, surprisingly, is the 2's cancel out. Right? So what we end up getting is square root of 2. So rationalizing the denominator doesn't always mean you're simplifying. It's really not the same thing. But in this case, it does actually simplify the result, right? 2 over the square root of 2 is fairly complicated, but when you rationalize it, it turns out that's just equal to the square root of 2. And that's much simpler, and it's going to be easier to work with. So now that I know what k is equal to, I want to plug that in to my formula, because k is a constant. It won't change. For this problem, k is always square root of 2. It will never equal anything different. However, a, l, and w will vary, so we don't want to leave these numbers plugged in for a, l, and w. We want to go back to using the variable names for those. But for k, we don't need to use k anymore because we know what that's equal to, and it's fixed at that number. So for step 3, we have a equals, instead of k, we're going to have square root of 2 times L times W. And now I'm ready to answer a question about this problem. And the question is, what is A when L equals 6 square root of 3 and W equals 1/6? So we're going to take these numbers and plug them in for L and W, and then simplify to find what A is equal to. All right, so I'll have A equals square root of 2, L is 6 square root of 3, W is 1/6. I'm sorry that's off the screen, but I just wanted to make sure I had room to write it. But there you go. Those are the two numbers I just plugged in here, so you can see that. And now I need more room again to simplify this, but I don't really need much room, honestly. So what's going to happen if you think of this as a fraction being over 1? This 6 on top cancels out with this 6 on the bottom. The 1s just go away because when you multiply or divide by 1, they don't change anything. So all we're really left with is square root of 2 times the square root of 3, which multiply together to give me the square root of 6. And that's the answer. All right, let's move on to the next example. Now this one's pretty tough. Suppose Q is directly proportional. So notice they use a different phrasing there, but it means the same thing as varies directly. Suppose Q is directly proportional to the square root of h. So not just h, but the square root of h. And inversely proportional to the cube of j. So not just j, but the cube of j. That's level 1, right? They're describing the relationship there. And like I said, it's customizable, right? Not only can you have different combinations of variation, but the thing it varies with can be customized. It doesn't have to just be a variable. You can throw other things in there, like square roots and cubes. So we're going to have to make sure to incorporate that into our formula. And Q equals 24 when H is equal to 4 and J is equal to 3. Find Q when H is equal to 4. That's a little bit silly to have H equal 4 again, but it's random, so sometimes it'll be the same number twice. But this time J equals 1/3. So that's going to change things up a little bit. All right, so it's a lot more complicated, but it's still the same structure. Level 1, level 2, level 3. So level 1, take this description and convert that into a formula. This time it's a combination. And as I mentioned, a good rule of thumb to follow is if it varies directly with something, you put that thing in the numerator, you multiply it to k. And if it varies inversely with something, you put that thing in the denominator, which means you divide k by whatever that is. And that's how you're going to set up the formula. So we're going to have, we don't have a formula to memorize and just switch out x and y for whatever's in the problem when it's combination of variation like it is here. We're just going to start with the variable that's given first, q, equals, and something I didn't mention before, but even with multiple variations, there's only one constant k. Now you could argue that each description of a variation has its own constant associated with it, but if you get multiple constants in the same proportion problem, they can just be lumped together into a single constant anyways. So even if we had one constant for directly, one constant for inversely, if you take two constants and multiply them together, it's still just a constant. So we're just going to keep it simple and just have one constant k. Right. Now for varies directly, we're going to put this in the numerator multiplied to the k. What's going to get multiplied to the k? It's not just h. Let me use a different color here. It's going to be the square root of h. Right, so it varies directly with the square root of h, so the square root of h gets multiplied to k. Then we're going to divide by the inversely part, right? So inversely, it's inversely proportional to the cube of j, not just j, but the cube of j. That's what we want to divide by. That's going to go in the denominator. So not just j, but the cube of j. All right. And so there's our formula. So that's how you construct that when there's combination of variation. Varies directly goes in the numerator, varies inversely goes in the denominator, and make sure you take into account the full description when you're placing those things in the numerator and the denominator. The square root of h, the cube of j. We use those descriptions here. I'm trying to think of how a good way to say it. We incorporated that into our formula. All right. And that gives me my formula. The second step is to find k. And to do that, we need to have the values of all the variables at one instance, which is what they give us next. And this is level 2. Right? So they tell us that q is 24 when h is 4 and j is 3. So we're going to plug all of these numbers into our formula. And then we can solve for k. Right? So q is 24. We don't know k, that's what we're about to find out. Square root of h, which is 4, over j, which is 3. And so again, kind of the arithmetic's a little bit tricky here. Not that these numbers they give us were difficult, but they're being placed in a difficult situation. So first I would start with simplifying the square root and the cube. And so we're going to get 24 equals k times the square root of 4 is 2, and 3 to the third power is 27. Right. Then to solve this for k, I need to get rid of the fraction, so I'll multiply the common denominator to both sides, which is 27. And you can see that this is going to turn into a big number. Right. So multiply 27 to both sides, and we're going to get 27, I made sure to have a calculator ready today, times 24, which is going to be 648. Equals k times 2, and then to get k by itself, you're going to divide by 2. So divide that by 2, and we get 324. So k is equal to 324. Now that we know what k is equal to, we're going to plug that number in for k into our formula. So we go back to using our variables, right? We want to go back to having letters here instead of numbers. But k gets replaced with the number that we just found because k is a constant. I know I've said it multiple times, but I'm going to say it again at least one more time. It's a constant, so it won't change. And so we don't need to keep k in there. We know what it's equal to, and it's stuck at that number. K will be 324 for this entire problem. However, q, h, and j are variables. They will equal different numbers at different parts of the problem. So once we're done with this set of numbers, we go back to using the letter representations so that we can plug in different numbers later. Right? So for level 3, we're going to have Q equals, we have K, which is 324, times the square root of H over J to the third power. All right, now, I'm going to go ahead and scroll up so we can see these numbers. We're ready for level 3. It's a good color to use here. I feel like I've used them all already. Level 3, which is to find Q when H is 4 and J is 1/3. So I'm going to plug these numbers in for H and J, and then I can simplify and find out what Q is equal to. All right, so Q is equal to 324 times the square root of H, which again is 4 in this case, over J, which is 1/3 to the third power. So you could just plug this into a calculator. Might be the easiest way to handle that mess. But if you're going to work it out by hand, here's how it's going to look. You simplify these first. Right? So we're going to get Q equals 324. The square root of 4 is 2. And 1/3 to the third power, you apply that third power to the top and bottom. 1 to the third power is still 1. 3 to the third power, we saw already, is 27. Now to divide by a fraction, this is the way I think of it. I'm dividing by a fraction, right? This fraction bar here is a division. So we have Q equals 324 times 2 divided by a fraction, 1 over 27. And how do we divide by a fraction? We multiply by the reciprocal. So let's switch colors again. So Q equals 324 times 2 times the reciprocal, which is going to be 27 over 1. Which again, the 1 can just be ignored. If you're dividing by 1, it just kind of goes away, and because it doesn't change anything. So we get 324 times 2 times 27. And you get this really big answer, which will make you, it's going to make you lose your confidence, because you're going to be like, wow, that's a crazy answer. Could that possibly be right? But for this particular problem, this is typical. You'll get these really large answers. And I know that because not only do I do this particular problem for the lecture, for my lesson, and it's on the homework, by the way, so this is a homework problem that you'll see if you're in my class anyways. I also put this question on the exam for chapter 2. So be ready for it, right? And you should be ready because you should have seen this 3 times at least, minimum, before you actually take the test. You're seeing it now in this lesson, because you should be watching it. You'll see it in the homework, and then you're going to see it on the practice exam, and then you'll have to do it on the test. So you should be really ready for this. Even though the numbers are kind of difficult, you'll have practiced it so many times that you should be ready for it when you see it on the test. And every single time you've done it, you're going to see the answers are just big numbers every time. So it shouldn't make you lose your confidence when you see that on the test. All right. Let's take a look at another example. So find an equation of variation where y varies directly as the square of x. So again, don't overlook that little detail. It's really important. The square of x. And y equals 54 when x is equal to 3 square root of 3. Now, maybe I'm doing this backwards because, on the homework, it's gonna go the reverse of what we've done in this lesson. You're going to have, the first few problems will just be level 1 problems, where it just goes to level 1. It doesn't go any further than that. And then the next set of problems you'll encounter will be level 2 problems, where it does level 1 and then level 2, and then it stops. And then the last set of problems are level 1, 2, and 3. I really did the reverse. I jumped right into those level 3 problems, so you can just get a picture. I just wanted you to get the big picture first of what's going on with these problems overall and what they're leading up to. And now I'm going back to do an example just to kind of show you what it looks like when it doesn't go all the way to level 3, how you should handle that, because it will feel a little bit different. But notice there's only 2 segments to this problem, which means there's only 2. Level 1, which is a description of the relationship, which will give me my formula. And then level 2, which is here's some numbers to plug in so you can find k, and that's it. They don't ask us a question. They don't say find y when x is equal to blank. So all we have to do is level 1 and level 2, and we're done. Right? So level 1 is going to function the same way as it did before. I see varies directly, and that's the one where I have a formula memorized. I just memorized that formula. Instead of y, well, there is no instead of y. We're just using y again. So I'm just going to keep y here. But instead of x, it's a little more complicated than, right? It's complicated than that. I'm skipping over words. It's a little more complicated than that, right? Because it's not just x, it's the square of x that we want there. Right? So it's still the same variable. It's a little confusing, right? Because they're still using x, but they're adding more to it, right? It's not just going to be x in this problem. It's going to be the square of x. Which, be careful with that. It's not the same as the square root of x. Those phrases sound really similar, and I notice students will get them confused. They'll put square when it says square root, or they'll put a square root when it just says square. And while the wording is very similar, you got to be careful about that, because really, if you think about it, they're completely opposite things, right? A square is the opposite of a square root. So you don't want to put the exact opposite of what's actually being said there. That's a pretty big mistake. So, all right. So this is level 1. We got a formula now, right? That matches the description that was given. Now we're ready for level 2. It's going to work the same way as the previous problems. We're going to plug these numbers in. So we have y equals kx squared. We're going to plug in 54 for y. And again, giving us a hard time with the numbers, we're going to plug in 3 square root of 3 for x. And so we're going to get 54 here for y. Sorry, I'm doing a really bad job writing my numbers. Let me try that again. All right. 54. That's still a bad. It looks like an S. Okay. One more time. 54. All right, good. Equals k. We don't know k. We're trying to find out what that is. X, which is 3 square root of 3. And then that has to get squared. And that's a tricky number to square, honestly. Again, if you have a calculator, that can really save you from making a mistake here on simplifying that. But I'm going to show you how to do it without a calculator. Because these are being multiplied, you can distribute the power of 2. I can't draw my arrows this morning either. You can distribute the power of 2 to each of these. Right, and we're going to get 3 squared. That was kind of a weird glitch. Oh, what is going on? 3 squared. When I hit the undo button, sometimes it goes a little crazy. 3 squared. And then the square root of 3 also gets squared. So each of them will get squared individually. Now 3 squared, of course, is 9. The square root of 3 squared, what happens there is the square cancels out with the square root. This is what I said a moment ago, right? These are opposite things of each other, right? The square root is the exact opposite of a square. They cancel each other out, right? And so when these cancel each other out, all we're going to have left here is 3. And these are going to get multiplied together. So we get 9 times 3, which is going to be 27. So that's how that works out. The k copies down now that we have that figured out, and it's still going to get multiplied to the 27, and it's still equal to 54. Now we can solve for k by dividing 27 to the other side. And this actually works out nice. So even though the numbers were a little bit unpleasant, once we get to this point here, we just get k is equal to 2. Right. Now that we know k, now in this problem, it doesn't ask us to state what k is, but some of these problems on the homework will say, what is the value of the constant k? So you would type this in first. You would say k is equal to 2. Then it's going to ask you, what's the equation? Now this problem just skips to that. It just says, what's the equation? You don't want to type this in because this is just the formula that models the equation you're looking for, but it's not really an equation until you know what k is equal to. So you have to find k first before you have the equation. So that's kind of the difference in terminology I like to use. While k is there, it's a formula that models the situation. But to turn it into an equation that models the situation, you have to find the value of k and plug it in. So now that I know what k is equal to, I'm going to plug that in to our formula to turn it into the equation that we're looking for. Right? So we're going to have y equals 2, because k is equal to 2, x squared. And this is the equation that models the situation, and that's what they want us to type into the box. And so that's what would go in here. Now they already have the y equals here, so all you have to type into the box is the 2x squared. And that would be the final answer. So be on the lookout. Sometimes they'll ask you first for k. If they ask you for k, they'll say k is equal to blank. You would just type in 2. Once you get that right, then it moves on to this part. And you would type in 2x squared. Not kx squared, not just 2, not 54. Sometimes students say, oh, y is equal to 54. It was only equal to 54 in this instance, but it's not asking for the value of y in that instance. It's asking for the equation. And so you'd want to type in 2x squared. All right. Let's see. So I have a couple more examples here. It looks like 3 more. So why don't we, you saw there's a couple word problems, which honestly are no different than the problems we've already done. There's a little more background information, but otherwise it's the same 3 levels. So what I try to tell students is you shouldn't think of these as word problems. They're no different than the regular problems. It's just instead of just saying X, Y, and Z, they have some background information that X is this thing, Y is this thing. But it's still find the formula, plug in the numbers to find K, then answer the question. That's all these word problems are. I'll show you in just a second. But what I was going to suggest is, why don't we have you do this problem? So pause the video. I'm going to pause the recording. I'm going to work this problem out, and then, off screen, off camera. So when you resume the video, you'll see the answer on the screen, and you can check to see if you got the correct answer. Okay, so here is the answer. T varies sorry, I said varies, but that's not what it says in the problem. T is inversely proportional to y. So inversely, since that's the only variation, it makes me think of the other formula I have memorized that we haven't really had a chance to use yet in this video. Y equals k over x. Right? It's not directly this time, it's inversely, so you want to use the inversely formula. Except instead of y, we have t on the left-hand side, and instead of x, they actually want to use y on the right-hand side. And so your formula becomes t equals k over y. That's level 1. Level 2, we'll plug in these numbers. We'll plug in negative 40 for t. We'll plug in 3 for y, which is what you see over there on the right side of the screen. And now we can solve for k. We do that by getting rid of the denominator. Multiply the common denominator to both sides. It's kind of hard to see, but it's right here. We're multiplying by 3. The 3's cancel out on the right-hand side, so we get k by itself. And on the left-hand side, 3 times negative 40 is negative 120. So that is the constant of variation. That's the proportionality constant. And that's actually what they're asking for first. So in this box here, it's asking for the constant. So you would type in negative 120. Once you answer that correctly, it will ask for you to write the formula, or what I've been calling the equation, once you've plugged k in. And so you want to plug negative 120 in for k, and you get this equation. And then that's what you would type in for your next answer. And so you should have t equals negative 120 over y as your equation. And that's where it stops. So this was just a level 2 problem. It didn't go all the way to level 3. It only went to level 2. All right, let's take a look at a couple of word problems. The time required to process a shipment of oysters varies directly with the number of pounds in the shipment and inversely with the number of workers assigned. If 3,000 pounds can be processed by 6 workers in 8 hours, then how long would it take 5 workers to process 5,500 pounds? All right, so again, a lot of information there. There's this whole story behind the numbers, but it really breaks down to the 3 levels that we talked about before. So I'm pretty sure every word problem is going to be a level 3 problem. Find the formula, figure out the constant k, then answer the question in the word problem. So the first sentence is just level 1. They're giving you a description of the relationship between the variables, and from that you can construct a formula. The big difference with this particular word problem is they do not give you letters to use as your variables, which means it's entirely up to you what letters you want to use. So you can go with the generic X, Y, and Z, or you can use letters that are more descriptive of the thing that they're representing, which is what I prefer to do. So here, the time required, that's our first variable. So we have to be able to identify what the variables actually are here. Time is the first one. And I think T would be a great letter to represent that variable. So I'm going to use T there. Varies directly with the number of pounds in the shipment. So the number of pounds is your next variable. We could use P for pounds. Now some students will use N for number, but then you also have number of workers. So N would be a little confusing. You might forget which in you're talking about number of pounds or number of workers. And so I would use P for pounds. And inversely with the number of workers. And so we'll use W for that. Once you've decided what your variables are and what letters to use, you can ignore the background information, at least for this part. So let's reread the description, but with only the variables. T varies directly with P and inversely with W. So it's just like the problems we were doing before now. Right? It's a combination of variations. So there's not really a formula for me to memorize and just switch out the letters. I have to kind of just construct. I guess you could memorize the y equals kx over z, because that's the standard combination one anyways, and that's what they're using here. But I like to just kind of construct it from scratch, if you will. All right, so we'll start with t equals, there's always one constant k. For varies directly, we multiply by that variable. It goes in the numerator, however you want to think of it. So P goes in the numerator multiplied to K. And for inversely, we divide by that variable. It goes in the denominator. So W varies, how do we say? It varies inversely with W, so W goes in the denominator. And there's your formula. Right? Just like the problem we did. This is really similar to the problem that we did earlier with Q, with the big answer, right? Q and H and J, except simpler because we don't have to do square roots and cubes and all that stuff, right? So there's level 1. Level 2 is let's find what K is equal to by plugging in numbers for these variables. As long as we know T, P, and W simultaneously, we can figure out what K is equal to. And that's exactly what the next piece of information is about. If 3,000 pounds can be processed by 6 workers in 8 hours, now, you kind of have to go back to the background information to know where to plug these numbers in. Which variable do they need to be plugged into? 3,000, that's the number of pounds, so that's P, can be processed by 6 workers, that's the number of workers, that's W, in 8 hours, that's the time. All right, so plug those numbers in for those variables. We have 8 hours, we have 3,000 pounds, and we have 6 workers. Now I can solve for K. And this might look kind of bad, but actually you can divide these. 3,000 divided by 6, I guess it cancels out with the 30 there, but it's going to give me 500. So I get 8 equals K times 500. So again, you could use a calculator to do that. 3,000 divided by 6, you get 500. Then you solve for K by dividing 500 on both sides. And what's going to end up happening is you get a fraction, which I actually, normally I don't recommend this in algebra, but for this situation I think it's pretty helpful. You can plug into your calculator and you'll get a decimal. So we're going to take 8, and it's actually not a bad decimal. Now, if we got like a run-on decimal, like 0.158372, then we probably just want to keep it as a fraction. If we got a repeating decimal like 0.33333333, like 1/3, probably want to keep it as a fraction in those cases. But this one actually works out to be a nice terminating decimal that we don't have to round off. We end up getting, I guess I'm going to continue over here, 0.016. And that's it. I'm not rounding it. It just literally ends at 6. And so that's the value for K. You don't want to round this off. You don't want to truncate the numbers. So if it's a decimal that does run on for a long time, you need to keep as many decimal places as possible. Because if you round that off, your final answer is not going to be exactly correct. Okay, now that we have K, we can plug that into our formula to make this equation for level 3. Right, so T equals, instead of K, we have 0.016 P over W. And now I'm ready to answer any questions they might have, and they do have a question. How long would it take for 5 workers, so that's W, to process 5,500 pounds? That's P. And we're looking for T. So we'll plug those numbers in. T equals 0.016. The number of pounds is 5,500 over the number of workers, which is 5. And this is something I can just dump into my calculator. I already have the 0.016 in my calculator. So times 5,500, divide that by 5, and we get 17.6. So again, not a perfect answer. I don't know, perfect meaning not a whole number answer, but not a horrible answer either. It's just one decimal place. And again, I'm not rounding. It literally just ends at the 6 there. And so that's hours, right? So we would estimate that it would take 5 workers 17.6 hours to process 5,500 pounds. And that would be the answer that you type in to Math Excel. All right, we got one more problem. We're hitting about the hour mark, which is a pretty typical length of time, it seems like for me, with these videos. I think for this one, it's another word problem. Let's have you guys try this one. So pause the video. I'm going to pause the recording. And off screen, I'm going to work out the solution here. And then we'll both resume, and you can see the answer that I came up with and check to see if you came up with the same thing. All right, so the cost C of steel tubing varies jointly as its length L and diameter D. So in this particular word problem, they actually do specify the letters that you should use for the variables, even though you don't have to use them, but that's what I used. If a 3-foot tube with a 10-inch diameter costs $210, find the cost of an 8-foot tube with a diameter of 7 inches. So I'm sorry, I should have read the problem before I asked you to pause the video. So the first step is to get the formula. It varies jointly, so I thought of y equals kxz, and then I replaced x, y, and z with the letters actually given in the problem. So instead of y, we have c. Instead of x, we have L. Instead of z, we have D. That gives me my formula with the variables that they provided in the problem. Then that's level 1, right? I have the formula. Level 2 is to find the value of k. And so I take the numbers that they gave me here, plug them in. So 210 for the cost. The length is 3. So again, you have to kind of identify what variables these should get plugged into. The diameter is 10 inches. And then we solve for k. So 3 times 10 would be 30. Divide that to the other side. You get k is equal to 7. Plug that into the formula. So now you have this equation you can answer the question with. Right? So now you have this equation that you can answer the question with. Sorry, I'm having to repeat myself because I keep messing up a word here or there. So the question is, how much would it cost for an 8-foot tube with a diameter of 7 inches? So we plug in 8 for the length, the diameter 7 inches, and we we just simplify this to find C. And so we multiply those together in our calculator and we get $392, right? So the cost would be $392, excuse me. Let's just go ahead and end this video now. So that was the last example. That concludes the video for section 2.6, which is also the end of chapter 2. So if you are a student in my class, you should now start preparing for the chapter 2 exam, which will be the next thing that you will have to do. And so I haven't made it yet, but I plan to eventually make a review video for the chapter 2 test. So that'd probably be the next video that you will want to watch. Thank you for watching, and I'll see you in the next video.